the speakers are giving questions there. But the secretary sent a link, so now I'm just not sure if people will want to. Yeah. Oh, probably I need.
Laser, you tap to see the pointer on the previous screen, but it's okay.
They just so maybe there will be. Did you want a cup of water? No, just. Here's a couple of Vietnamese places. This is a good one. This is like the Cajun place.
Oh, the Cajun style.
Yeah, probably one of the Houston specialty.
Jaden taught me this.
Jaden Newstead. That we took him to this place. Is that there's one of the local cuisines of Houston, Decay. There's a large Vietnamese population that is close enough to So.
Not just the mystic of the southern somehow there.
Oh, right. You just throw that out here. You just throw that really go down into the what time? Oh, it's 6:30. Where is? Don't make me slack at you people. May 20th. 2021. More.
Oh,
At least remember to change the price.
that's a good catch.
Mhm.
So I'm living in the past.
Anybody drop by to bug you while in class? I'm encouraging the students to stop it. Yeah, check that. Assignments. All right, sounds good. Let's keep going. So, yeah, we're happy to have Doojin Kim visiting today. Doojin drove down from Texas A&M to where he is working as postdoc, where he's super important postdoc, who single-handedly runs the Mitchell conference and keeps the entire show working at the Mitchell Institute. And he's around yesterday and today, so I'm going to chat with him. We've got a couple more hours before he's driving back home tonight. And in the meantime, he's going to tell us about his recent work on probing axion-like particles with neutrino experiments. Go for it.
Okay. So thank you so much for the invitation. Well, actually, this is my first time to be in right stream. Yeah, very pleased. I'm very pleased to share and discuss my recent research subjects together. So as you know, the Andrew just introduced, I'd like to discuss the probing axion-like particles in the various neutrino experiments. So by the way, in my talks, I will use the terms axion and axion-like particles interchangeably, but most of the times I refer to more generic axion-like particles, not restricted to the particular QCD axions. So okay, so the talk is based on the set of the papers, my research papers, and I briefly discuss the essential ideas of those the studies. So some of the discussions are might be less detailed. Therefore, if you have any questions during my talk, so please feel free to interrupt me and ask your questions. Okay. Okay, so here's the outline of my talk today. So I begin with the discussing the motivations of axion-like particle physics, and then I overview some existing axion-like particle searches, mostly focusing on axions interacting with the photons. I also briefly discuss the importance of lab-based the ALP searches. In the next part, so I will talk about the role of the neutrino experiments in terms of axion-like particle searches, and then describe the production and detection of axion-like particles in neutrino experiments in a more general manner. Once that is done, I discuss the search proposal in the context of a few the example experiments, particularly focusing on the DUNE experiment. So if time allows, I would like to discuss, there's some the global features and the other, the search channels before concluding my talk. Okay, so today I'm not going to talk about the main ideas and the detailed theoretical aspects of axions and axion-like particles, but I would quickly say that the QCD axion is a viable solution to the strong CP problem, and relevant physics programs have been extended to the more genetic, the pseudoscalar axion-like particles, and therefore the axions and axion-like particles receive a lot of attention for a long time. So indeed, they are one of the major drivers to motivate the physics beyond the standard model. In particular, given the null observation of new heavy resonances in popular models like the supersymmetrical extra dimensions, I think the axion or the axion-like particle searches and related phenomenology are receiving a lot of particular attention these days as an orthogonal direction to find the new physics. Okay, so in fact, the axion-like particle searches lie in low energy the frontier as compared with new heavy resonance searches performed in the energy frontier facilities like the LHC. Therefore, the many the ongoing and proposed low energy experiments are potentially the sensitive to the associated signals. Moreover, the upcoming interceptive frontier facilities, including the next generation Neutrino, will provide us with unprecedented opportunities to probe these the feebly interacting species. Okay. So sometimes the axions and axion-like particles are discussed in the context of the photo scenarios. So where the dark sector particles are connected to the standard model, the sector particles through some sort of the photons, and axions or axion-like particles play a role of such a photo or mediator. So in that sense, axion-like particles, the searches can be naturally connected to even the dark matter search program. So now restricted to flavor diagonal operator dimension 5 operators, for simplicity. So the interactions in the axion polar is given in this Lagrangian, and this the Lagrangian can be straightforwardly extended to the genetic pseudoscalar mediators and or axion-like particles. Now, in addition to the polar context. Okay, so we shouldn't forget the various excesses, anomalies, and non-minimal dark sector scenarios. Okay, so for example, some models of the axions and axion-like particles have been proposed to explain the various unresolved experimental issues that are shown here, and also some of the some scenarios of the relativistic dark matter produced in the present universe predict the existence of axions and axion-like particles. Of course, some of the excesses are not significant anymore. For example, the Xeno wanton excess, as you know, and some axion interpretations are challenged by other arguments. But I would say, the axions and axion-like particles are well-motivated candidates you would immediately have to think about to address all of these issues. Okay, so now we see that the axion-like particles are very well motivated. So then the peptide the search experiment. Okay, so interestingly, most of the search techniques are based on the photon coupling described by this dimension 5 operator. Of course, the other couplings of the ALPs the equally interesting and the worth investigating. for example, the out electron coupling and the out the nuclear coupling, etc. Some of which they could arise at the root level in the presence of this output coupling. Okay, but however, throughout my talk today, I will just the focus on output coupling, assuming that the other couplings are simply negligible. Basically, we can get some general idea from this discussion. Okay, so one of the most famous methods, search method utilizing the output coupling is the solo axion, the search that's done by flux, such as the cast SR. So basically, there's plenty of the photons. There are plenty of the photons inside the CERN, creating a enormous the flux of axion-like particles. So once they reach the board of the cast magnet, some of them they can turn into the photons, which can be detected by the photon detector. Well, you can directly produce axion-like particles in the lab using a laser. For example, in the so-called the light shining through bulb experiments. Okay. So basically, the high intensity laser shines on an optical barrier through the magnetic field region. If a photon that turns into the axion-like particle by the external magnetic field, then the axion-like particle can pass through the optical barrier and enter the another magnetic field region beyond the barrier, whereas the typical photons cannot by construction. Right? Now, if this the axion-like particles is converted back to the photon, then you can interpret that, okay, so actually the axion-like particle was produced and then came into the second magnetic field region. So then here the accessible the mass range is essentially set by the energy of the laser. So it is typically restricted to the EV scale or even below, although some of the X-ray laser experimentation sort of being planned.
Question?
Yes.
The photon that's produced on the right side, is that going to be the same frequency as the photon on the left side?
You mean the frequency here?
Yeah, the photon that's produced on the left side, is it identical to the photon that was initially on the left-hand side?
Yes. So here in most of the cases of energies, still the same. So the energy of the photon here, the energy of the axion here, and the energy of the photon here, they are the same. So the the frequencies are essentially the same. Yeah. Okay, so there's another class of the lab-produced arc searches in Windows. Okay. So basically, a high-intensity particle beam is impinging on a target, creating a bunch of the photons, and some of the photons can turn into the axion-like particles through the so-called premature process, which I will explain a bit later. Some of the if the produced axion-like particles decays into the photon pair within the detectors, then you can essentially observe the decay signal. So here since the decay, the axion-like particle decay is essential, the ALP they should be heavy enough, and the coupling shouldn't be too small. Otherwise, you wouldn't observe the decay signals. Okay, so these type of experiments are sensitive to high mass region. Okay, so I have to quickly overview a few representative experiments. But in addition to the various in addition to these experiments, the various astrophysical and cosmological considerations have set the limits on such axion-like particles. And indeed, as you know, they have already ruled out a wide range of parameter space, so that there may be vector searches cannot reach the beyond those limits unless that they are aiming at probing the highness the region. So then the question you may ask is what would be the justifications of the lab-based the research effort? Well, I don't know the best answer to this question yet, but nevertheless, I would like to emphasize that lab-based researches are less model dependent, hence more robust, whereas astrophysical and cosmological consideration would be more model dependent. Okay, so maybe you can make minor modifications on your axion model such that axion production mechanisms have the non-trivial dependence on environmental parameters like the temperature, mass density, etc. Or you could imagine some non-conventional supernova explosion mechanisms. Okay. So indeed, the necessity of lab-produced the arc searches goes in the context of the clay Kubela's the anomaly in 2006. Okay, so the preferred values of the ALPs and the couplings are inconsistent with the astrophysical bounds at the time. They're causing a huge discussion the how to make the ALPs compatible with the existing bounds, and encouraging people to modify the conventional ALP models. So it's the Kubela's anomaly. I don't know the details of the experiment, but it's sort of the white incident experiment. So they said that in the field case, and they observed some non-trivial the signal, but then it turns out that the preferred values are inconsistent with the astrophysical bounds. Test only ruled out the current region, and then issue was the solution of observation of the bounds. But at the end of the day, they found that that kind of access is possible. So that's okay. Okay, so I still, but here I think still this episode is definitely the same important message that the lab-based researches are not only performant considerations, but more conservative and robust. Maybe outside for physics might be higher involved, and then Okay, so just to give you an idea, I here collected the existing constraints for lab-based constraints for the output coupling. So you see here there's the huge the white regions that had to be re-explored or explored in the lab. So for these the purposes, I recommend to discuss the new channels of new sources of the Axion-like particles and various channels available, especially at neutrino experiments in the rest of my talk.
So it looks like can you bring your screen here? So it looks like the energy of ALP with these big energy. Move the little green bar.
Yeah, okay. All right. So let me move this green bar here. Okay. Is it better?
Okay. So what's KB?
So KB is here. Yeah.
So you're not showing the astro limits.
Right. So these are just the lab-based limits. Yeah. So like that.
No one does anything with nuclear physics?
That's a good question. Well, but these are the other limits. So what kind of the other limits? Yeah, maybe,
I was wondering specifically if anyone has used, do you know what Moss power?
yeah,
Heard this?
no.
It's a fact where you have emitted gamma ray in sort of, I don't know if you have it by cross section. This is right. section. And just some weird.
Oh, yeah, so if nobody's actually done that,
It's probably doesn't work for some reason. But nobody does like nuclear physics science.
yeah, so yeah, I mean that's an interesting the best. But I think that's very interesting. Okay. Okay, so now the question is why we should take care about the neutrino experiments. What's the thing with that? Okay. Well, there are some the compelling reasons that I have personally thought about. So hopefully you'll be also convinced and agree. So the first, so these the experiments are capable of the copiously producing not only neutrinos but the photons, which may create axions or axion-like particles. And second, the same experimental setup that can be used for studying not only neutrino sector physics, like in neutrino oscillation and the sevens, but axion-like particles. And then finally, as I mentioned just before, the searches at neutrino experiments can provide complementary information in exploring the relevant product space. So in this context, I have chased the ALP detection potentials in a wide range of experiments, from reactor, the stuff the pion source to the beam focused neutrino experiments. So from the left to the right, the typical energy of the axion-like particle source particles, they're increasing from MeV scale for the tens of GeV. So here the different energy scale allows for accessing the different mass scales. So I also try to show the complementarity among these experiments. Okay, so there are much more neutrino experiments. Okay, so here's the partial the list of the beam and experiments. So the first three the experiments are the proton beam, low energy proton beam experiments, where the neutrinos are produced from the decay of the stuff pions and muons, and then the other the proton beam experiments that use higher energy, the proton beams, so that the produced neutrinos and potential axion-like particles are more energetic and moving in relatively forward direction. And the last three are the example of the electron dots. So here, the summarize these experiments in terms of beam energy and the beam intensity, target type detection, technology, etc. Based on which you can gauge, the best, the search strategies and expected sensitivity, etc.
This is a mix of existing experiments and
future. Yes, right. So existing and the future.
Sorry, what does it coherent? Is that an angle of 90 degrees?
Yes, the coherent is the stuff the pion experiments done in the coherent experiment the day observed the sevens scattering.
Yeah.
For the first time.
I see stuff. I guess that's
Yes, right. So hopefully okay, so as actually suggested by the Lagrangian under consideration, photon is I mean, as I keep saying, the photon is the major source of the axion-like particles here. So in the sense, it's crucial to estimate the photon flux as precise as possible. So this is the expected, the photon flux in energy and the angle from the beam axis. The based on the simulation for a megawatt scale DUNE-like experiment, including the cascade photons and photons from megan decays. Well, of course, that depends on the underlying the external details, but these simulation results suggested roughly 10 to the 23 photons are actually produced inside the target per year in a DUNE-like experiment. So here I put the same effort to collect the information of the ongoing and the proposed the reactor experiments, like the thermal power technology, etc. Just like in the neutrino experiments, let me show energy spectrum at the reactor neutrino experiments. So the minor collaboration in Texas A&M, performed the GEM simulation for the megawatt scale. The reactor, including cascade photons and photons from isotope decays and nuclear deexcitations, etc. And this is the expected the photon flux as a function of the photon energy. So now you see that this simulation tells that actually 10 to the 19 photons are produced inside the reactor core per second. So if you think about,
How well is this known? I would guess that the 10 to the 9 is known, but it's not known.
so you mean the
I mean the spectrum, like how well.
so you mean the systematics? You're concerned about the systematics, whether the shade is precise.
You mentioned reactor neutrino, sterols, all this other stuff before. And there was this huge saga, like people trying to react neutrino fluxes from neutrino fluxes. And then just every different team that calculated that.
You mean you're talking about the anomaly?
Yeah, so but all of these are assuming different nuclear processes are happening, and then I'm guessing it's the same processes or similar processes that also can be photons.
Okay.
I'm just wondering, like, you know, how well is this known?
Well, here, so I don't know whether they included that kind of observation in their the simulation. But I guess they are irrespective of the existence of that anomaly. The message is the huge number of the photons are produced there. But maybe the shapes might be different.
Because this is just trying to predict all the different nuclear physics that's happening. Here, might also be.
Yes. Well, let's see. So then,
I mean, in other words, how are you confident of this spice of surface?
so that's I think the nuclear characteristic like surface nuclear deexcitations.
Also, there are energy lines. There are some energy lines in this spice.
Right.
But how well known are those?
Yeah, that's a good question. How well known those are. So I guess some of the processes are well known, right? So some of the deexcitation or yeah, I agree that there are some uncertainties there. And that will be the change spectrum of.
I was just wondering, because if you just took a GEM for simulation, most part this you might get it right for your own like where application. So if you ask someone radiation weapons for what you expect to be.
Yeah, okay. Okay. So I think that's an interesting point. Yeah. Yeah, we'll have to think about it. So anyway, so Yeah, so the 10 to the 19 photons. I mean, I would say, you know, the photons are, you know, enormous number of the photons are produced. They are potentially the source of, you know, and if you think about, you know, the gigawatt scale, how much of, you know, the reactors, you can imagine 3 orders of magnitude, you know, photon plus. So okay, so now so we now know the you know the photons are you know produced copiously in various, you know, neutrinos. And let's discuss the how research. So here I've worked on, you know, the genetic the formulation, which you know that for your own purposes, irrespective of your underlying details. So suppose you have a source particle that can produce, or you know, depending to the axion-like particle. So your photon. So once the photon is converted to the axion-like particles, then it should be, you know, the safely delivered to the detector of interest and leave you know, some experimental or observable signatures in the detector. So therefore, if you know the production probability, transportation probability, and detection probability, then you can say that the final probability of the signal observation for a given source particle is given by the product of these the 3 the probabilities. Okay, so then let's discuss, you know, the whole procedure. You know, the beginning with the production, followed by transportation and detection. Okay, so again, as I keep saying, you know, the photons are you know, important in this business. So that actually, you know, the several you know, photon production channels. So like in user stories, the photons are you know, the striking the target, creating a, you know, the set of hadrons. Among them, the neutral mesons like piezo or the atom mesons decay to the photon pair. There's another important contributions from the secondary charge the particles, for example, like, you know, the ionized electrons. So they basically you know, go through complicated, you know, the cascade, you know, ENM cascade, the processes, the creating a bunch of, you know, the photons. So now the production of the meson that can be described by the standard event generators like you know, Harvey. Okay, and then you know, this is the main you know, the production mechanism that you can find in most of the you know, the pheno studies. However, it's hard to estimate the photon flux from the cascade, the processes, so using a standard event generator. So so more dedicated to simulation, I mean, the simulation is needed to describe the production cascade photons inside the target. Now, for the reactors, the beam, the particle is irrelevant, but photons, you know, photons are coming from you know, nuclear deactivations, either decays and cascade photons initiated by nuclear fusion, the processes. So again, the standard you know, event generators cannot describe the situation inside the reactor. So again, you know, more dedicated detector level simulation is needed. And or you could consider the photon flux at reactors with the existing, you know, the literature like this, you know, the paper for your, you know, initial estimate. Okay, so now for you know, the given the photons, so axion-like particles can be produced by you know, the pre-Markov the process with the atoms inside the target or you know, the reactor core, as I briefly mentioned earlier. Okay, So the production cross-section is volume and given by this expression here. So now you see there that the production cross-section is enhanced by the coherence factor z squared. Okay. And in principle, I mean, basically this, the pre-Markov process competes with the standard model, the interactions of photons, like the pair conversion. So basically, the probability, therefore, the probability, production probability, is given by the ratio of signal production cross-section over total the standard model interaction, the cross-section plus the total the signal, the production cross-section. So here in the numerator, I put the fiducial, the cross-section, meaning that you can just consider the ALPs, the moving toward the detector, because the ALPs not traveling for the detector don't contribute to your final signal sensitivity.
Yeah. I think this is become more relevant aqueous question because see that production cross-section depends on the energy of the photon.
Yeah,
so if you miss small spectrum of photon, then you can underestimate your production.
Yeah, so that's right. So here the production cross section also depends on the energy. So let me see. Is that the case?
It depends on
right. So the T. Right. So the E gamma. But then the forward direction, this is mostly vanishing.
Yeah, you only use photon.
Yeah. I mean, the most of the events are produced in the forward direction, right? So then this part is relativistic limit. This part is sort of, and you get some like a singularity, like a structure. And I guess then in that case, it's okay, right? So probably the production process doesn't too much depend on the energy. Well, but then the number of the photons matter, right? So if I overestimate the production rate of the photons, then I would overestimate the signal sensitivity. And if the other way around happens, then if I would underestimate. Yeah. Okay. So yeah, actually, yeah, that's an important point. We better check whether we can trust the photon flux from this unless we the tune production rate. So is it possible to measure the constants of man? So we can discuss it. Okay. So once so axion-like particles are produced, it should survive until. So then what would kill axion-like particles? So basically, in principle, the ALPs can scatter on the material inside inside the particle or the reactor core, or they just decay to the diagram. So therefore, the ALP should neither interact in the target or the reactor core nor decay before reaching the detector. Okay, and then these are described by the exponential law of the mean decay length and the particle decay. So the mean decay, mean free path, yeah. So the mean free path of the axions are typically much longer than the typical length scale of reactor core and target. So then the first probability is typically the unity in most of the well-motivated quantum space. And then you can just care about the second the probability in most of the phenomenological studies. Okay, so the ones they reach the detector safely, then they should leave the signatures inside the detector. So broadly speaking, there are three channels, the detection channels, like through their decay, through their scattering, through their conversion. Okay. So the first the channel is rather traditional, as most of the studies you can find they consider the ALP detection through their decays. Whereas the other two channels are sort of the rather brand new, some sort of brand new the channels proposed recently in the context of and reactor neutrino spins. Okay, so let's discuss these channels one by one. So so in the decay channels, so basically the ALPs they should be heavy enough, and the couplings should be small. Okay, so then the decay the width of the axion-like particle is well known, as shown here, and then the detection probability is simply given by the exponential decay law. Okay, so again the all decay is essential here. So so therefore the resulting the sensitivity covers the regions of heavy enough ALPs and the not small the couplings. So like heavy mass regime and the large the coupling region. So when it comes to the second channel, so the axion-like particle can interact with the nucleus via the inverse spin-off process, as shown in this diagram. You just switch over the process diagram, and then detection probability of the scattering is given by the scattering target number density and fiducial axion-like particle scattering cross-section, and the times the length of the sweeping distance that the axion-like particle would travel for. So then the DC is actually useful in probing lighter axion-like particles whose decay rarely happens. Right. So if the decay channel is useful for the ALPs, which can decay earlier, but then if they are long-lived, then the channel you can think about is the scattering. So in this sense, this channel the complements the decay channel. And finally, the conversion channel involves the ALP to the photon conversion in the magnetic field region. And my collaborators and I recently proposed the idea of using this conversion channel in the experiments, having the magnetic field region of their detector systems. And then the conversion probability is given by this. The conversion probability in the relativistic limit is given by this expression, where the last two factors are the form factor reflecting the coherence of the conversion. So basically, if the mass of the ALP becomes large, then this the form factor becomes negligibly small, so that your conversion probability becomes negligible. So if the mass of the ALP is small, then the conversion probability becomes large. But then it's as you increase the mass, then it's decreasing. Okay, so now we are ready to calculate the axion-like the event rate of the rate of the signal the events. So again, for a given the photon, you can calculate the production, the probability, transportation probability, and the detection probability in whatever the channels you prefer, right? So then the product of these three probabilities is the final probability of the signal observation for that specific photon. And then you can calculate these probabilities for a sufficiently large set of the injection the photons, and take the average the value, and this is the average acceptance or the signal detection efficiency. And then you simply multiply this, the average, the acceptance by total number of the injection photons, and the final number is the expected the number of the signal events you can expect. I mean, the expected number of the signal events, the given exposure. Okay, so now let's discuss the search proposal, example search proposals. Okay, so again, the beam focused the fixed target experiments. So as I explained earlier, so basically the photons are impinging on a target, creating a setup of the hadrons, and then the neutral measures decay to the photons, etc. And also the charged the particle, any charged particles get through the ENM, the showering processes, creating a bunch of cascade photons. And then the photons, they can turn into the axion-like particles through the pre-Markov process. Then the produced axion-like particles get through the focusing or the shielding and enter the detectors and live where they lead the experimental signatures through the decay, scattering, and conversion. So these in these experiments, in this class of experiments, relatively, the high energy particle beams are used, and energetic photons allow for the production of the heavier axion-like particles. So here, since that particle beam is energetic enough, so the large the beam energy allows the axion-like particle flux to be more or less the directed. Okay. Well, actually, in this case, the focusing horns so don't play any the role in terms of the signal production. The recently my other collaborators and I pointed out that the charge measurements, which could be affected by the focusing horns, there can be the important sources of the axion-like particles depending on the underlying model details. So so we are now currently working on the more detailed analytical studies. So hopefully so the paper will come out pretty soon.
The idea is that the decay within the target material, so the photons scatter on the target material.
Yes. So the charge, well, neutral measurements are the decaying very promptly.
Yeah. So the charged ions, they photons, they axions in the shielding or something.
So actually, okay. So let me give you a little more details. So once the charge measurements are produced, and then I think that here the target is not like a thick, like a thin rock, something like that, and then they are escaping from the target and then getting into the focusing horn. So depending on the horn currents, like a positive the measurements or the negative measurements are focused, the other diverge. But they are a bit longer lead, and then they are flying and then focus, and then eventually decay to the neutrino and the lepton and the axion-like particles. Right. So you can attach the axion-like particle to the lepton leg or neutrino leg or the pion leg, depending on the underlying model details. So then the pions are focused, but then the axion-like particles are also focused. So you can essentially have the focused axion-like particles. So beam of axions. Yes, exactly. So so then you can essentially increase the flux of the axion particles. So anyway, so in we consider the DUNE experiments. So in the DUNE experiments, we will have liquid argon time projection chamber and the gas phase argon time projection chamber. The liquid phase, the detector comes with a 75 ton active volume, and gas phase, detector comes with the magnetic field in the detector. And we investigated the axion-like particle searches in the scattering channel for the liquid phase detector. and the out searches in the decay and the conversion channels for the gas phase. Also, we recently proposed the idea of the target list measurement mode for the DUNE for the reduction of neutrino backgrounds. So I will discuss this thing a little more in a few slides. Okay, so here's the our sensitivity estimates in decay channel, scattering channel, and the conversion channels. So as I said earlier, you can see there are some complementarity in those three channels. So the decay channels are decay channel is good for the probing high mass rigging, right? Whereas the conversion the channel is advantageous in probing very light the axion-like particles as the conversion probability gets maximized. And then the scattering channels are good for the mass regions in between the channels.
On the supernova constraint, why did that constrain GA channel?
So supernova, I think as far as I understand, I guess the media the Andrew knows better than I, but I think the supernova, if the supernova is exposed, then if there's something there, then
So what we have like is it from the neutrinos?
Yeah, I think they if you have okay, so so far I have just focused on the signals, but not this as much. Oh yeah, I mean, so there are actually the backgrounds, but not many, but the various the neutrino backgrounds. Okay, so for example, the neutrinos in the scattered off via the nucleus, creating the single the pion, which decays to the photon pair, or neutrinos neutral current, the interaction, the scattering, that would to produce the recoil electron, which could be misidentified as photon. So basically, the neutrinos are the major the source of the backgrounds to the axion-like particle signals. So if there's a way to suppress the neutrino production rate or the effective neutrino production rate, so then you can essentially increase improve the signal sensitivity. This is the material used in the beam. Yes, very much. So to tackle this issue, so we recently proposed an idea of movable target system for DUNE, like a dumping all the protons directly to the dump area, originally inspired by off-target mode data collection collaboration. So like in the standard mode, there's a target, and then the photons are hitting the target and they're creating the charge measures and the neutron stellar. But you just to get rid of the target, or then move the target, and then the beam is directly going to the dump area. So so you can expect the many gains. So most importantly, you can expect the significant reduced neutrino induced backgrounds, because in the dump, all the particles are supposed to be stuck or lose energy, so that even if you produce the neutrinos there, their energy is less energetic than the neutrinos that produced in the target mode, and also their probably the angular spectrum is more. Their flux is spread over the angle.
Well, will be the same for the actions.
So axions.
Yeah.
Well, in this case, the axions are produced by the SPA photons, and the photons from the neutral measures, and then the neutral measure leads or their kinematic behavior. I would say that they're roughly the same as the target.
Oh.
Okay. It's not. They're probably decaying before seeing other areas. In addition, the distance between the source point and the detector becomes a little shorter, and then you can the more the signal, the flux is expected to enter the detector. So at the end of the day, without reducing the background and enhancing the signal, effectively enhance the signal, so that the resulting signal or background becomes large. And finally, the measurement allows us to confirm or disprove the non-neutrino sector nucleus signals. Okay, so if the nucleus signal is neutrino sector related, so then you wouldn't observe any the excess of the signals in the off-target mode measurement, because the neutrinos sector related physics should come from the charge measurement decay, but in the target mode, right? So all the target measurements are observed, or they're less energy based. So okay, so again, as I said earlier, the neutrinos are coming from the charge measurements, and these are the energy spectrum and the angular spectrum of the neutrinos in the off-target mode. Okay, so now you see. Well, the first we observed that the Janssen simulation tells that not all pions actually decay. So roughly 2/3 of the pions observed to the dump through some inelastic scattering processes, etc. So only 1/3 of the pions effectively decay to the neutrinos. And then you see they're very small, the production rate of high energy neutrinos. And also, neutrino flux is more or less isotropic, not focused, right? So in that sense, the effective amount of the flux getting into the detector, effective amount of neutrino flux getting into the detector is very small. Since the muon, the neutrino is the dominant. The muon neutrino flux for the dump mode case and the target mode case. Okay, so these are the energy spectrum normalized to 10 to the 20 photons on target, and these are the muon neutrino spectrum in the target mode, and this is the muon neutrino spectrum in the off target mode. Now you can clearly see that neutrino the flux is significantly reduced in the off-target mode. For more quantitative, the comparison here we show the ratio of the off-target mode neutrino flux to the target mode the neutrino flux. Then you see in most of the relevant energy regime, 3 to 4 orders of magnitude are suppressed. So based on these other simulation, we found that roughly 0.5 electron only events with half beam power and the 3 months exposure. Okay, And then even the pi zero, single pi zero resonance production, that becomes even smaller. So essentially, background free the search, is possible. Okay, so here's our sensitivity estimate. Okay, so these the blue lines are our the expected the sensitivity reach in the target mode that I showed earlier, and then the red lines are our expectation of the sensitivity reaches in the off target mode. Again, we assume the 3 months and half beam power, but they already you can reach the better, you can achieve the better sensitivity because basically off target mode enjoys roughly the background free nature. Okay, so I already running out of time. Okay, so yeah. So okay, so in the second class of the experiments, I mean the second class of next class of the experiments are Sept and Neutrino and the beam duplex experiments. So I mean the idea is simply the same because the focusing horn that doesn't work in the previous case, but these class of experiments using 1 GeV the particle beams to produce Sept ions, and the beam intensity is typically larger than that of beam focused experiments. And then since the beam particle, the beam energy is small, the axion-like particle flux is sort of an isotropy, okay? But the detectors can be placed closer to the source point, so effectively you don't lose the signal flux much, okay? So we investigated the signal, the sensitivity of the CCM and the Sept ion facility and the DAMSA at a the rare nuclear isotope accelerated the facility, and these are our expecting the sensitivity reaches. Well, so because the beam energy is sort of the small, so then it can reach the high mass regime, but depending on the experimental design and the schemes, you could actually place the detectors very close to the detector with the appropriate the background projection schemes, so that you could actually probe the rather promptly decaying the axion-like particle the parameter space. And the last class is class of experiment is reactor neutrino experiments. Okay, so again the photons intensity is huge, okay, but then the photons are soft, but the soft photons allow for probably low mass axion-like particles. And again, just like just before, the axion-like flux is isotropic, but the detectors also that can be even placed even closer to the source point, so we can get a lot of the signal flux.
Meters from the core. So the scale.
The meter scale. Well, the minor is 4 meter.
Oh,
Yeah, and I think a solid is 10 meter, and then I also consider the 8 meter scale. But yeah, many of the reactor neutrinos, they are like 10 to 20 meters or something like that. But yeah, I mean, I just maybe exaggerate this. So anyway, so I can see that we investigated the ALP searches at reactors, and also we also investigated the ALP searches at ISDAR because these even if this is using the particle beam, production and detection schemes are conceptually similar to reactor between experiments. And then these are the expected the sensitivity estimates. Okay. And this gives you over the global picture. So a lot of yeah. So a lot of the groups are working on this, and you need to get on board. Okay. So yeah. So yeah, actually the huge the opportunity is here. So if you have a very smart idea to cover this region, you're gonna be a star, I think. Also, I just talked about the output on the couplings, but again, the main idea is straightforward. They're applicable to other, the channels like the the electron coupling, nuclear coupling, fluon coupling. So a lot of groups, and including myself, have worked on various channels. Okay, so and then I would say, the neutrino experiments, allow us to deploy almost every single corner of the space. Okay, so let me summarize my talk. Okay, so I just want to let you know, read these conclusions. So hopefully, you've got a plan for your research, future research projects based on what we discussed today. Okay, okay, that's it. Thank you so much. Yes.
For your CCM studies, this is a neutrino experiment, right?
Yes. Start the pioneer neutrinos.
Are you playing the same game as you did with DUNE, where you're trying to remove the neutrino background in this case in favor of the axion signal?
So in the DUNE. Here?
So for DUNE, you played this game, right, where you tried to minimize the neutrino signal.
Right.
In favor of also the neutrino background.
Right, neutrino background.
In favor of the axion
Yes,
signal.
yeah, that's right.
Did you play the same game with CCM when drawing your model?
So yeah.
Consider the neutrino background.
So actually, that's a good question. So these kind of experiment, well, okay. So basically, the beam focused neutrino experiments is the features the large distance between the source point detector. So with a high intensity with the beams, and then essentially you create a lot of neutrons. And then neutrons are neutral, and then they and so that they're hanging around and making backwards. But it's okay. So the distance is huge, and then neutrons don't make the same effect. They don't create but then these guy is different, right? So the CCM, as I said earlier, so their detectors are very closer and close to the source point. Let's say the 20 meters or something like that. Then their the intensity, is like the 10 to the 22 per year, and then a lot of the neutrons are hanging around. I mean, I know the other CCM, so they try to put a lot of estimate the neutrons of the backgrounds. So yeah, so in that sense, it's a bit the tricky to I mean, the question is whether we can enjoy the other background.
Yeah.
Basically, it's possible, and I think the CCM collaboration is trying to achieve the background. Initially, they wanted to protect away, but they realized that so sizable, more complex. So then
It's also like the systematic as well, isn't it? That they're trying to sort out, because from the last time I read about it, it was like a 5% leeway in terms of these, VRM, this VRM background.
right. So that is the one of the reasons if you want to suppress the finger, you can't do the estimate because neutron flux estimation itself is challenging. So that's why they want to suppress freak of the system. So I don't know whether that means more systematic
maybe out of time. Yes, yes. Yeah. I want to ask if you talked to this idea of couplings. Yeah. Yes, they wouldn't like that.
That experiment is all about neutrinos.
Yes.
Actually, I talked to well, the part